Assalamu alaikum dear students, we're back with another video lesson. In the previous video lessons we were talking about magnetic force on a charged particle or magnetic force on a current conductor. Today we'll talk about the applications of magnetic force on a current conductor. One of the first thing that we have is a loudspeaker. So we're going to talk about what are the parts of it, or the basic parts of a loudspeaker, and also we'll learn about how it works as well. So applications of the magnetic force on a current conductor or wire, the first thing that we have is a loudspeaker. Now, what are the parts of a loudspeaker that you need to know? Remember, for the loudspeaker, the parts are you can see that is a coil, and there's also, you can see that that's a cone or a paper cone that is attached to the coil, and then there is also a permanent magnet here. So what exactly, or how does it exactly work? Let's talk about this. Where the base of this speaker work, and we can say that it is the electro or magnetic force on a current conductor. So how it exactly working? Now let's talk about each one of these in details. First of all, let me just redraw this one with the parts of a loudspeaker one more time. So we can say that this is a permanent magnet, and there is a coil here. Basha. This coil obviously is mounted on a soft iron core, you can see that. So let's just draw some coil in here. Okay, so here's a coil. And obviously this coil, you can see that, or there is a paper cone that is attached to this coil. And when there is a magnetic force on this coil here, this paper cone, it is going to vibrate or move back and forth. This vibration here, you can see that, obviously it is going to make the air or cause regions of, let's say, compression and rarefaction regions here. And then this is how exactly it can cause or create a sound here. All right, so let's talk about the first thing that we have. We can talk about speaker or loudspeaker. All right. Loudspeaker. That means it is a magnetic force on a current conductor. So the first thing to happen, let's say there's a person who's talking, Basha. This person is talking here, obviously. Now, clearly that there is, for example, this sound goes to a microphone here. This microphone, you can see that it converts, we can say, this electrical or this sound signal here, or this sound energy into electrical or varying electrical signal, Basha. So we can say here's sound. This sound that goes to the microphone, Basha. Now obviously there is a diaphragm. There's still, this is something like a diaphragm here. I don't remember the exact word here, that when this pressure of a sound goes into this, it makes it vibrate. Obviously there's a small coil here, but that coil changes the sound here, these compressions and rarefaction, into an electrical signal here. So we can say there's a sound signal. That sound signal here, using a microphone, will be converted into a varying, into a changing electrical signal. Basha. Kata ish microphone baba change sound energy, yeah, sound signal to electrical signal. But electrical signal it is varying, it is changing. Basha. It goes to an amplifier. What does exactly amplifier do? Basha? Amplifier, obviously from the name, it converts this small signal here to something way bigger. Basha, these are, let's just convert or write something smaller than this here. Let's say these are sound signals in here. So it converts these sound signals to something like bigger here, so that it can amplify the sound here. And then from this amplifier now, it goes to the loudspeaker here. So now this loudspeaker, obviously now, it is going to convert this varying electrical signal into what? Back to sound energy again here. So how does it exactly works here? Let's talk about this a little bit more here. So inside this loudspeaker, Baba, this is, we have, like we said, we have a coil, and then there's a permanent magnet. There's this paper cone here as well, exactly. So let's say this is north, right? And let's say this is south. There's another north in here. So once this varying electrical signal goes to the coil, Baba, now there is a current flowing through the wire of a coil. Even if it is a coil, if it is inside a magnetic field, obviously there's a magnetic field in here, right? Magnetic field, there is always going from north to south. You can see that these are providing, for example, a magnetic field for the coil to be in. magnetic field permanent magnet. When a current is passing or flowing through this coil here, obviously this current is varying, as you can see here, alternating, Basha, and varying, changing. There will be a force, Basha, a magnetic force on this wire that carries current here. A magnetic force ودكات بابا coil كي move دكا باشا. And we can say it vibrates the coil. Basha? Yeah, and it makes the coil move back and forth because it is vibrating, and also it is changing here. This force here increases and decreases. That decrease force with, of course, let's say this, it changes or moves the coil back and forth. Also, vibration, and now it can be transferred to the paper cone here. A paper cone is that is now vibrating, Basha. The paper cone is vibrating, and we know that once it vibrates, of course, now it can produce the sound here. And this sound, of course, that because the electrical signal here, it is exact electrical signal from the sound here, يعني an exact signal from the sound here, the sound that we hear, it is exactly the same of the person who's talking. Basha. This is a kind of like a basic or a summary of how a speaker works. Basha baba. Kata bas agar goti main principle like what does the speaker on? Agar levi baba. It works and based on what thing it works. It works on a magnetic force on a current carrying conductor inside a magnetic field. Basha. Kutman basha kani permanent magnetic man here, coilic man here, legal paper conic, which is attached to the coil that it can vibrate once the coil is vibrating. Man katika كرنتك بنا كل كده ضربات كسر صار a magnetic field وقشمان قتيش ما بشتري هر كاتك if there is a current that carries current inside a magnetic field أو كاتي there be a magnetic force on it. A magnetic force وده كل كم move be بس كل is attached to the cone, then the coil or the cone is vibrating or vibration the beat the sound. Bash baba. That is the only thing you need to know regarding loudspeaker. Bash kata loudspeaker use magnetic force to produce a sound. The loudspeaker uses magnetic force acting on a current carrying wire in a magnetic field to produce a sound wave that one in blood. Bashakani loudspeaker baba gutman koilak man here, permanent magnetic man here, like soft paper cone, which is attached to the coil that acts as a speaker. This is like, for example, how it works. But before that, you can see that in a loudspeaker, when the direction of the direction and the magnitude of the current in the coil of a wire is changing, the paper cone attached to the coil moves. Because the sound signal that is converted to electrical signal that is alternating and varying and is changing. Once, of course, that goes to the coil, it makes the coil vibrate and move, which produces a sound. Now, in steps, if we, for example, follow the steps one more time, in a speaker system, sound signal is converted to a varying electrical signal. Step here, by using what? By using a microphone. It converts sound signal to electrical signal, and varying electrical signal. This electrical signal that is amplified, and you go to the curtain and sent to the loudspeaker here. And then obviously, the loudspeaker, this varying electrical current causes a varying magnetic force. This magnetic force on a coil also increases and decreases because we said that earlier. Magnetic force, BIL. The stronger the current, the stronger the force there on the coil here. So this alternating force causes bubbling on the coil, results in a vibration of the attached cone, which produces vibration in the density of the air in front of the paper cone and the speaker. And of course, in this way, an electrical signal, it is converted back to the sound wave that is closely resemble the sound wave produced by the source in here. Says what does the operation of a loudspeaker depends on? It depends on a magnetic force on a current carrying conductor. Conductor magnetic field there will be a magnetic force on it. That was the first application of magnetic force on a current carrying conductor. Now another application that we have is a galvanometer. What is made of? Let's talk about galvanometers a little. Normally galvanometers is a device that is used to measure small amount of current. So a galvanometer, we can say, it is used to measure small amount of current. Galvanometer, right? It is a device used to measure small amount of current. Small amount of current. In what range, Baba? In a range of milliampere to microampere. You know that milli is 10 to the power -3 and micro is 10 to the power negative 6 ampere. This is how small, let's say, the current should be for a galvanometer to read that or to measure that. So what exactly a galvanometer? What are the parts of a galvanometer? Masha, let's talk about this a little. So the parts of a galvanometer, the first thing that we can say it is there is a permanent magnet at both sides here. Let's say one of them is north, the other one is south. And then there is also a coil, Basha. There's a coil, or there is a coil that is mounted on a, there's a coil or a bunch of wires here wrapped around this coil right here. And then there is a soft iron core that is mounted here. And then there are, we can say, some labels here where a galvanometer can work on. So there's this needle here, this needle that is connected or attached to a soft iron core here that can be deflected once there is a current that is passing through coil. So now, one more time, the parts of a coil are, well, I mean, the parts of a galvanometer. We can say a coil, Basha. The first one is a coil. The second thing is, what am I saying? The first thing is a permanent magnet, Basha. The second thing is we can say a coil, Basha. The third one, you can see that there is a soft iron core that is mounted, so it is pivot, so that it can pivot freely or so that it can rotate freely once there is a current flowing through the coil here. That obviously connected to the needle here. So this would be the third thing here. The fourth thing that we have is there is a spring that is connected to, Asha, there is a spring that is connected. Of course, you could draw the spring in a different way here. Let's just write this one a bit nicer. There's a spring that is connected to the needle so that when there is no current, actually, let's just draw this one in a different way, perhaps a little different from what is drawn in the book here. There is a spring here. Okay, let's just draw this a bit nicer. Okay, so there's a spring here that once there's no current in the coil here, it brings the needle back to, let's say, 0 point in here. So what exactly, or how does it exactly work, Baba? We can say that this galvanometer needle, it works on, let's say, obviously this is one of the application of magnetic force on a current carrying wire. So when there is a current is flowing through the coil, Baba, which is inside a magnetic field, there will be a force on it. So this magnetic force, but because this coil is not moving back and forth, instead it's rotating, so now you can call this magnetic force, you can say that it's providing a torque in here, Basha. So this torque, it rotates the coil or the needle here once there's current flowing through the circuit. And by the way, this needle deflection, Basha, deflection, it is directly proportional to the strength of the current that is passing through the coil here. In other words, the more the current in the coil, that means the more the needle deflection. This is how it works, Basha. So what happens when there's no current in the circuit? Then this needle will be brought back to the 0 point by this spring right here. So this would be the fourth one, and that is the spring, obviously, there. This is what exactly a galvanometer is and the job of this galvanometer. Now, later on, this galvanometer can be used as a meter and voltmeter. That'll be next, but let's just go through this one more time. My galvanometer is a device that can be used in both construction of voltmeters and ammeters. We'll talk about this next. But then galvanometer, galvanometer or a galvanometer, we can say measures very small currents, Basha, in a range of what? In order of milli to micro. How does a galvanometer work? It operates using electromagnetic force, Basha. But this magnetic force, because it causes rotation, we can call it a torque. How is it produced? Produced by a magnetic field acting on a current carrying wire, Basha. What are the parts of a galvanometer? The galvanometer, or what does it consist of? It consists of a coil of wire, Basha, that is the first one, a soft iron core mounted so that it is free to pivot in a magnetic field, and then also a permanent magnet and also a spring to return the pointer back to 0 when there's no current through the circuit. The torque experienced by a coil, rotation force rotate beat is directly proportional to the current in the coil. This means that the larger the current in the coil, obviously, the greater the torque and the more the coil will rotate before the spring tightens enough to stop the movement of the pointer. Also, we said that the amount of deflection in the needle is proportional to the current in the coil. What happened when there's no current? Gutman, the spring will bring the needle back to 0 point here. Basha, this one, obviously, this is also a diagram of or a picture of a galvanometer here. Okay, what else do we have? It says galvanometer can be converted. That is also another point here, Baba. But normally, galvanometer can be used to measure small currents, right? Or galvanometer, that is a device that let's say, measures small amount of current in order of milliampere to microampere. This is how small it is. But this same galvanometer can be used as an ordinary ammeter or an ordinary voltmeter. Adi ammeter voltmeter sinababa. Ammeter is a device that measures current, normally high current, and voltmeter is also a device that measures high potential difference. But the voltmeter or galvanometer that reads or measures small amount of current, actually can be converted to both ammeters and voltmeters. How? Let's talk about this one. So let's say galvanometer. This galvanometer can be converted, Basha, to both ammeter and voltmeters. Basha. So how can it be used as a ammeter or as a voltmeter here? Ammeter. We can do that, Basha, and a voltmeter too. Let's write this one too. And a voltmeter can be converted as both ammeters or two ammeters and voltmeters. How can we convert a galvanometer to ammeter, Baba? By connecting a resistance, Basha, by connecting a resistor of low resistance, Basha, by connecting a resistor of low resistance, Basha, of low resistance, but it has to be connected in what? Connected in parallel. It has to be connected in parallel with the galvanometer. Parallel. Let's just say parallel. That has to be connected in parallel with the voltmeter. Rasha, so how exactly? This is a galvanometer. So this is a galvanometer. And if we connect a resistor of low resistance in parallel, resistance very low, in parallel with this galvanometer. Now this galvanometer can be used as an ammeter. Now this is how you can do that. Basha, what about how can we use a galvanometer as a voltmeter here? Baba will say, right, by connecting a resistor, but this time of high resistance, Basha, high resistance, and also has to be what? Has to be connected in series, Basha, with the voltmeter. How exactly? Let's say this is the voltmeter, okay, galvanometer, right? If we connect a resistor of high resistance with this galvanometer, now this galvanometer can work the same as a voltmeter now, Basha. So it can do the job of a voltmeter. Now let's talk about each one of these in details, and also we'll talk about the series and parallel circuits as well, Basha. The first thing to talk about, Baba, is how we're going to convert or use a galvanometer as an ammeter here. So here's a question, says how a galvanometer can be used as an ordinary ammeter. Ordinary, Baba, a normal ammeter. We said that by connecting a resistor of very low resistance, but in parallel with the galvanometer, then it can be used as a what? As an ammeter here. Now we have something else. This low resistor here that we're talking about, this one, it is called a shunt resistor. So what is exactly a shunt resistor, Baba? All right, so let's say this is galvanometer can be converted to as an ammeter here. How do we do that? First of all, Gutman, there is this ammeter. Now you can call this an ammeter. You have to connect a resistor, Basha, of very low resistance to that. We also said that this resistor has a very small value here. Basha, Gutman, this resistor must be very small. Now this galvanometer can work the same as an ammeter here. So we can say that this is basically part of or how it is. Now I need you to know one thing here, Baba. Gutman, remember this small resistor, by the way, it draws most of the current here. And where does or how do we know this? Because we already know that the relation between current and resistance is inversely proportional. So if the resistance is very small, then the current that is passing through this component or this part of a circuit is going to be very large compared to the other one here. So this small resistor here, it is called shunt resistor. What is it called? Shunt resistor. So what is shunt resistor, Baba? We can say it is a small resistor that draws most of the current of the circuit here. A small, Basha, a small resistor that draws, Basha, draws, yani allows most of the current of the circuit to pass through that one. That draws most of the current, of the circuit. Masha? Now, the next part that I need you to be aware of, Baba, this is parallel circuit. Whenever you see or parallel circuit, and by the way, what is the difference between series and parallel circuit? Let me perhaps maybe summarize something regarding that as well. If we have a circuit that all the components are connected one after another, Basha, and then there is one loop here. So this is, we have a battery here, Basha, positive, negative, and there's one loop you can see here, and all the devices are connected one after another. These are resembling a light bulb. That's not important here, but you see that there's only one loop here, one path for the current to flow here. So this is called series circuit. What about parallel circuit, Bob? In parallel circuit, there is more than one loop or one path for the current to flow in here. So for example, positive, negative, we have different light bulbs here or different devices connected, let's say, with the circuit in here. So you can see here there's more than one loop here, one path for the current to flow in here. So we call this one parallel circuit here. Okay, now after you know the difference between parallel and series, Baba, so here's what we're gonna do. Come on. All right, let's erase this one and this one too. Okay, now, since you know the difference between these two circuits here, how do we convert? How do we use a galvanometer as ammeter? Good man, if we connect a resistor of low resistance in parallel with the galvanometer, now this galvanometer can be used as an ammeter now. So remember this, Baba. In parallel circuit, these notes are very, very important. I need you to be aware of them. In parallel circuit, Masha, you need these three study tips here. The first one, remember that in parallel circuit, Baba, the voltage is always the same. So V total is the same as the voltage over the galvanometer, or you can call it ammeter, doesn't matter at this point here, and then which is going to be the same as the voltage over the resistance here. Masha, that is one of the first things you need to know. And if you had any other components in the circuit, of course, the voltage over them is going to be the same. So there's no difference between the voltage at any point that you take in here, because in parallel, the voltage is the same everywhere. Now, the second thing here, the current is additive. What does it mean? That means I total, if you want to know the total current of the circuit, that is equal to the current that is over the ammeter or the voltmeter. Since we wrote voltmeter, let's just keep that, or keep it that way, and then plus the current that is passing through the resistor here. If we had any other loops, of course, we would have added this, but since we only have this two, we'll say the current or total current that is equal to the current that is flowing through this galvanometer, Masha, since we wrote ammeter here, so let's just keep that in mind, or so that it doesn't cause any confusion here, Masha. So let's say the voltage over the ammeter here, and this is the voltage or the current over that is passing through the ammeter here, plus the current that is passing through the resistor here. And then the third one here, it is always what? Always use, Basha, use what? Use Ohm's law. Ohm's what? Ohm's law. For every component, and for each component, Babylon, for each component. What exactly this means here? Okay. Now, what is Ohm's law here, Baba? Ohm's law, V dakata tse, yanish R doesn't matter here. V dakata IR. And if you want to, of course, rearrange that, later in chapter 6, we'll use this the most here, V over like this format. But it doesn't make any difference now because these are literally the same thing here. So this is Ohm's law, V, the voltage potential difference, Basha, it is equal to the current times the resistor. Now, how are these three study tips help us to answer questions related to this, Basha? Now, of course, we have a question. Let's jump to that question, and then after that, we'll talk about how we can convert a galvanometer to to a voltmeter basha. So remember, these are what we have. Gutman, how can we use a galvanometer as an ordinary meter? By connecting a resistor of low resistance in parallel with a galvanometer. Gutman, addition to resistor, it is a resistor that draws most of the main current, allowing only a small part of current to pass through the ammeter so that it can work just fine. Gutman, direction current, relation current to resistor. These are obviously inversely proportional. And one more time, this is a summary. You can say that we can convert a galvanometer to an ammeter by using a galvanometer plus a resistor of very small resistance, but it has to be connected in parallel. Was regarding the study tip, remember the 3 study tip that we've used. This is part of how we can convert it to a voltmeter, but that'll be after this question right here. We want to use as an ammeter, right, use an ammeter of internal resistance of 5 ohms here in order to measure electric current of intensities up to 10 ampere. While the ammeter measures currents between 0 to 1 ampere, what is the resistance of the shunt resistor that should be connected in parallel? It also tells you in parallel with the ammeter in order to do this job in here. What does exactly this question say? It says we want to, use an ammeter here. This is an ammeter to measure a current, to measure a current of intensity up to 10 ampere. Up to what? Up to 10 ampere. So up to 10 ampere, that'll be, we can say I total here. So what is I total? It is 10 ampere. But the question tells you that the resistance of this ammeter here, it is 5 ohms, 5 ohms. Now this ammeter here can read, currents up to, let's say between 0 to, it can measure currents between 0 to 1 ampere. We always use the maximum value, that doesn't benefit us from the calculation here. So we'll use 1 ampere. This is how much, or the maximum current that can pass through the ammeter. So the question says, what should be, for example, the value for the shunt resistor that needs to be connected in parallel, with the circuit so that it can do the job in here. Now, first of all, I need you to know one thing, total current only 1 ampere can pass through the ammeter. اگر 1 امپیر بره دا بڕوە بخۆمان چەندمان هەیە دا کەواتە چەندی بە ڕێستەرەکەیدا دەڕواتن. In this case, of course, the current that is passing through the other part or the other branch must be what? Must be 9 amperes. You agree with me on this thing, right? Very, very good. کەواتە دووبارە دەکەنە بابە ئەگەر 1 ئەمپێر بەناو ئەم ئەمیتەرەیدا بڕواتن کەواتە the current that is passing bubbling through the resistor یان bubbling the other 9 ampere should pass through the resistor here. Kata, this is one thing I need you to know here. Kata, that has to be 9 ampere. Let me just perhaps maybe draw this one again. Yes. If one is passing through the meter, kata 9 dika, basar resistor yan banaw resistor da Basha. If you remember the 3 study tips, Gutman, first one was voltage is the same everywhere, but I don't have the voltage at this point. The second one, Gutman, it is additive. That is also something we need to know. But if you start, for example, from the 3rd study tip, Gutman, use Ohm's law for every component. If I use Ohm's law, what do I get in return here? I'll get the voltage here. So voltage, Gutman, the current times resistance. The voltage that I'll get here, that'll be 5 volt. The voltage, Baba, the voltage across the ammeter here is equal to 5 volt. Because in parallel circuit, the voltage is the same everywhere, right? So, I get voltage later 5 ampere, 5 volt baba, later share 5 voltage. The voltage is the same everywhere. The voltage here is also 5 volt in here. If I have the current and if I have the voltage, can I find the resistor? Yes, using Ohm's law for this component too here, V the IR. R كده كانت اسمها كانت V over I V كمان 5 ohm 5 volt current كمان is 9 ampere So once you divide the two here, what do you get? You get 0. What is it exactly? 0 point something. Let's get a calculator. That'll be about, how much is this? 5 divided by 9, it is 0.556, or you can say 0.56 by rounding, Basha. 0.56 ohms by rounding. However, now go resistance or resistor, which is called shunt resistor. We see how small it is. Basha, let's summarize this one more time, Baba. See what exactly we did right here. Malera, summarize the chizol khira. Basha, lira, amiterik manaya. Basha, good malera, resistoric manaya. Basha. This is how it goes. Man, the total current that I have, Baba, lira 10 bonia. Bisarek b'khoy pedala resistance amiterik lira 5 ampere. 5 ohm. Also, the question tells you that the current is passing through the emitter. It is 1 ampere. That's that. And by the way, the total current is 10 amperes, Basha. So if one of them is passed, or 1 ampere passes through this, kaka, di 9 kedike, but she datarwa, 9 kedike, bere datarwa. Basha baba, I got leave. Lera قلت مان له هر كومبوننت شي عنده هر بشه شي يوز اومز لا لera كرنت ورستاس ماني بابا قال اومز لا بكاربين فولتج دبينو باشا فولتج دكاتا 5 فولت باشا وقلت مان parallel circuit بابا voltage is the same everywhere اگر voltage لسر او component 5B طبعا دبي ليرش 5B because that is a property of بابلين parallel circuit كاتا voltage ليرش 5 فولت كاتا ليرا فولت current دوباره اومز لا لو component بكاربينو بابا current معناه لقى voltage معناه you can find the resistor and that is what the question is asking for. ما ليرا resistance دكاتا سن دكاتا V over I ليرا جماعة كان multiply and bubble and divide of course you get 5.6 or let's say 0.56 ohms and that'll be the resistance of the shunt resistor. That is how easy you can do that. باش بابا اگر ناخذ كريك ليرا فولتج قديتو دتواني بلاي فولتج شي بابا فولتج اميتر كده دكاتا فولتج ريزستانس كي ليرا voltage عادة using ohms لا دكاتا IR ليرا شان عينا اي بابلن اي شنت ريزستر كي ليش دكاتا IR باشا ليرا كرنتا كمان يك الريزستانس كمان 5 يا ليرا كرنتا كمان دبيتا نو ريزستانس كأنه you could of course find the resistance here as well. That is exactly the same thing in both cases, whether you do this method or you do that method here, that's totally fine and you can do that. Basha, Baba. Now let's talk about the next thing that we have, Basha. Now let's go back to the other question. How can we use a galvanometer as a voltmeter here? Basha Baba. Good man. We could do that by connecting a resistor of very high resistance in series this time, Basha, with the galvanometer here. So Zara, how do we or how can we use a galvanometer as a voltmeter? Man, we could do that, Baba, by connecting this galvanometer or by connecting a resistor with this galvanometer of very high resistor, Basha. So now this can be used as a voltmeter now, Basha. This galvanometer can be used as a voltmeter now. But why exactly do we have to use this, Baba? Mano galvanometer na 20 voltage chi exagor bikhinta ka tagara voltage hemambu because voltage is directly proportional to the resistor here according to Ohm's law. Ka ta'alir hatsandi resistance kay ziyatir bi Baba voltage ka sir resistor kay gawrat bibi. Griman we have let's say 100 voltage Basha. So most of the voltage will be over this resistor here, Basha. So only there will be small amount of voltage over the galvanometer so that it can work safely without burning out, Basha. This is how we can do that. But yakdush mane Baba in series circuit agar lebi yakdu study tipi di kaman hay series circuit Baba. Just remember that the current is the same everywhere. So we can say I total is the same as the current over the, now you can call it as a voltmeter now, which is the same as the current over and passing through the resistor here, Basha. So this I total is the same as the current that is passing through the circuit, that'll be the total, is the same as the current that is passing through the voltmeter, and it's the same as the current that is passing through the resistor. Khali duam is rek aksi parallel circuit Baba. This time, Gutman, lewe current ka additive, Basha, voltage was the same everywhere. Lira, current is the same everywhere, but the voltage is additive. V total the bubble V voltage is voltmeter plus the voltage over the resistor here. And third step here, always use Ohm's law V دكاتة I R باشا for every and for each component باشا. This is how you can use a galvanometer as a voltmeter باشا بابا. أو سيستدي بجلبين مكا because it will help you to answer the question that we're going to solve now. أدو خالص لكن أخوات underline كبابا normally or normal meters are used to measure current, but what current? Normally high current. Voltmeters are used to measure potential difference, but what kind of potential difference? High potential difference, you can say. بشارة ما نحل كدو بابا استاذ بشارة وزارين ذكرنا وأبي إن شاء الله عندك اللي حلك هنا. But first, let's solve this question that is related of using galvanometer as a voltmeter here. So it says a moving coil voltmeter measures potential difference between 0 to 5 volt. Basha, Kawata, we can say that the voltmeter that we're using here, Baba, it can measure up to 5 volt. Basha. So let's do this one here. Watch this, Baba. So this voltmeter that we're going to use, it can measure up to 5 volt. That is what the question is saying, Basha. Or maximum voltage it can measure, it is 5 volt right here. All right, it says if the resistance of the voltmeter is 500 ohms, Basha. So the resistance of the voltmeter is 500 what? Ohms here. 500 ohms. Calculate the intensity of the current through it if it reads 5 volt in here. Basha Gutman, use Ohm's law everywhere, whenever each component here. We have the voltage or the potential difference. We have the resistance of the resistor, resistance of the voltmeter. How much current is passing through this voltmeter here. Basha, using Ohm's law, Gutman V dakata IR. When I dakata sibaba dakata V over R, which is 5 over 500, right? The answer is going to be 0.01 ampere. This is how much current is passing through this voltmeter right here. That is the answer of the first part of a question here. All right. What about the second part of the question? It says we want to use this voltmeter to measure potential difference greater than 5 volt. What is the resistance of the resistor that should be connected in series? Don't forget. Oh, it's gone. In series, Basha, with the voltmeter, in order to measure a total potential difference of 30 volt once, 30 volt, what would be the resistance if you want to measure a voltage of 150 volt? Let's do the 30 volt first, Basha. If we want to measure, let's say a voltage up to 30 volt, what should be the value for a resistor that we need to connect in series with this voltmeter so that it can do the job? So here, once again, this is the voltmeter, Baba, and this is the resistor. What is the value for this resistor that should be connected in series in order for this voltmeter to measure a total voltage of 30 volt, Basha? So can I call this one V total? Yes, V total is 30 volt. Amma previously got man a voltmeter, Baba. The voltage that is over this voltmeter is what? Wasn't it 5 volt? Yes. Basha, I get 5 volt, the said voltmeter KB, Baba. Even if you're not sure, for example, of course you can find out, because basically that has an internal, it can measure up to 5 volt. That is what it says. The resistor of the internal resistor of the voltmeter, it is 500. So you could find the current that is passing through this one to here. Basha. Now this is V total here. Gutman, in series circuit, Baba, the voltage is additive. Total come on 30. If the voltage for over this voltmeter, get voltage instead of voltmeter, pins volt B, Baba. So how much is left for the resistor or to be on the resistor? Obviously 25 volt. Let's get 25 plus 5. We get a total of what? We get a total of 30. Basha. وقلتش من كاتا voltage بابا اللي series circuit is additive. بس باشا قلت معنى resistance of voltmeter بابا 500 ohm بونيا. قلت معنى again you could do the current or the calculation again. أجرش نا current كمان ديتو قلت معنى current يبقى نا voltmeter كده بابا it is 0.01 ampere. باشا قلت معنى series circuit current is the same everywhere. كاتا قلت current ليرة 0.01 بيت بابا ليرش عينشتا 0.01 يعني كاتا we can say IR إيش ليرة أو current بناو resistor كيش داترا. It is exactly the same current here, which is 0.01 ampere. Basha, there is one more thing here. Kata, we have the voltage over the resistor. We have the current that is passing through the resistor. Can we find the resistance of this resistor? Yes, the V good man. We use Ohm's law for every component بابا. V دكاتة IR باشا. الريزستانس كده دكاتة سن دكاتة V over I V كمان سن 5 باشا. هذه current كمان سن بابا. It is 0.01 and this sorry the voltage is 25 my bad باشا. It is divided by 0.01. So once you do the math, of course, you'll get 2,500. All right, 500 ohms in here. So this is how big the resistor of the resistance, Basha, that should be connected with the voltmeter in series in order to do the job. أو بشا كم بابا بشا دو مش عين اشتغل زار اللي جاتي 30 فولت بيكا تسن بيكا 100 was it 150 باشا yes. So عين شقت معناه voltmeter كيا. What should be the value for the resistor that can do the job if we want to measure a total voltage or potential difference of 150 volt. Lera قلت مع بابا voltage قال صار voltmeter كيس 5 volt باشا 5 volt كات أقليرة 5 برواتيرة هذه only دي كده تسيت الريزستانس كيونه we can say VR دكاتة 145 and قلت مع current كتسمبو the one that is passing or flowing through the circuit current كناقرة بابا. Because if you do this one here, resistance 500. If you do this one, you can find the current. The V over R, 5 divided by 500. You still get the same current, which is 0.01. The current doesn't change. And then 0.1. Now, what would be the resistor of this one here? So if you use Ohm's law again, that would be V over I, which is 145 divided by 0.01. The answer is going to be 14,500 ohms, and this is the value for the resistor that should be connected in series with the galvanometer so that it can be used as a voltmeter. This is how easy you could do these questions. Just make sure you use the study tips properly, and that'll be it. Let's get back to some or few questions or Wrya questions. So that we can be done with this section here. It says, which of the following can measure high electrical current, Baba? It says high electric current. Man high, and its current, obviously that is an ammeter here. All right, which of the following can be used or can to measure high potential difference, Basha? High potential difference, that is a voltmeter. Basha. The very low resistance, Basha, that should be connected or which is connected in parallel with a galvanometer when converted to an ammeter. To be able to measure high current, it is called what? The very small resistance here, we call that shunt resistor. So that is shunt resistor here. All right, 4 says the galvanometer can be converted to a voltmeter by doing what? By connecting a resistor of dash with the galvanometer. But in order to use a galvanometer as a voltmeter, it has to be very big, all right? On very high resistance, should it be in series or parallel? It has to be connected in series in order to convert a galvanometer to a voltmeter here. The galvanometer can be converted to an ammeter by connecting a resistor of what? A galvanometer, watch this, Baba. Galvanometer to be converted to an ammeter. Resistor could be very small b in parallel got a very low resistance in parallel. That'll be the correct answer for this question here. Okay, now the next thing here that we have says if an internal resistance of a voltmeter is 500 ohm, it measures the potential difference between 0 to 5 volt. What is the resistance of the resistor that should be connected in series, Baba, with the voltmeter in order to measure a total potential difference of 30 volt? That's exactly the same as what we done, Baba. Asha, what about this one here? This is also very similar, but of course sometimes the numbers are different here. Should I solve these questions or no need? Okay, let me perhaps maybe give it a try. All right, let's get back to the other page and use this one. I'll solve this question for you. ده كان ضلن فيديو كده ايش هو بس قينا يلا بابا تماشاك. The internal resistance of a voltmeter. So we have a voltmeter. The internal resistance of this voltmeter is 500 ohms. Masha. It says measure potential difference between 0 to 5. Voltage of voltmeter baba can measure up to 5 volt. What is the resistance of the resistor that should be connected in series? That should be connected in series. Resistance that is unknown. Basha, and then series with the voltmeter in order to measure a total potential difference of 30 volt. Basha Baba. Kata lira V total كمان سنة. It is V total, it is 30 volt. Lira 30. Basha. If this one can read 5, if this one can read 5, kata, we can say VR be 25 في Basha. 25 plus 5, that would be a total of 30. So Basha, later VR man here, we can find the current here, which is equal to V over R. That is 5 over 500 Gutman. The kata tsanbaba, the kata 0.01. Is that current detail? This is the current, but in series the current is the same. Kata lira shayna shtababa 0.01. Now is that you have the voltage, you have the current. Can you find the resistance? Yes. Resistance the kata V over I. V command 2.5 washan 0.01 the kata 2,500 ohms, and that's this easy, Baba. There's nothing difficult about this one. Now let's try the second question too, since we've started already. It says an ammeter of internal resistance. Internal resistance it is 5 ohms, Basha. Can measure current between 0 to 1, Basha. Oh, can I take this ammeter can measure, it is the maximum value, it is 1 ampere, Basha. 1 ampere. Basha. What is the value of the resistance that should be connected in parallel? What is the value of the resistance that should be connected in parallel with this ammeter, Basha, so that this resistor here that is unknown to measure a current of intensity of 21 ampere, Basha. So the total current that we have, it is 21 ampere, Baba. You can call this one I total. Basha is 21 ampere. If only 1 ampere can pass through this one here, if 1 ampere can pass through this one, let's just write it. The current that is passing through this one, it is 1 ampere. If 1 ampere passes through this, then the rest will pass through the other circuit, right? So we can say the current that is passing through this part here, it is going to be 20 ampere. Basha. Resistance mane baba. We can find the voltage. Voltage the kata I times R. 1 times 5, the kata 5 volt. Kata the voltage of this on the ammeter here, right? Voltage is ammeter 5 volt. Because it is parallel, the voltage is the same, Baba. Later 5 volt be kata voltage later same. We can say VR is also 5 volt. Basha. Is that you have the current, you have the voltage. Can you find the resistance? Yes, let's do that. So resistance the kata V over I. V command 5, current the command 20. That is obviously 1 over 4, which is equal to 0.25, right? That is going to be ohms here. Let's see if we have 0.25 ohms. And that is obviously going to be option A. All right, now section review Baba Pisara Nazozo Rasana. The particle mane obzan page nakaten, our charge kaiti, experience magnetic force mane right hand, whatever it is. If the speed of the particle is this much, what is the magnitude of a magnetic field? The particle passes through. Madam particle baba magnetic force dakata Q VB madam perpendicular no need to for sine theta. Actually baba magnetic field magnetic field dakata magnetic force over QV Basha. You do the numbers, you can find the answer is going to be 0.081 Tesla. That would be the strength of a magnetic field in here. An electron is moving north. Electron, it is also moving north, encounters a magnetic field. If the magnetic field points east, what is the direction of the magnetic force on the electron here? Make a table if you remember. There are magnetic field man here, V man here, there is magnetic force here. An electron moving north, direction motion it is Y positive. If the magnetic field points east, east yani east yani XC positive, magnetic force the Z. It is either Z positive or negative. Let's bring this one here, see how it was done before. So remember, so that you can get the same perspective. This is the direction of the bubbling motion, the direction of the motion here, which is north. Magnetic field it is X positive. This X positive, this is the direction of the motion. Direction magnetic force on an electron is the back of the hand. It is, we can say that it is pointing out of the page or Z positive. That is the direction of a magnetic force Z positive لير اللي بروي east to west وشتانا ما بكارينا. You can say upwards here. باشا. Or Z positive. See which one is given. For example, if it is given like in X and Y, you can keep that. Z positive أكاريشنا Z positive يعني upward. بسارش ماني بابا. That's also easy. باسي straight wire دكا أجر length كي وند بي أقال لي converti كا. Current كي وند magnetic field كي. What is the magnitude of a magnetic force on this segment of a wire? Because it is a wire, because magnetic force on a wire that carries current that got the BIL and bill. Also do the numbers and that's it. Two parallel wires of let's say charges moving in the same direction here. If the charge is moving in the same direction, so it could be both upward or both downward, it really doesn't matter. As long as the charges are the same here, that means the current is the same. So the question says, is the force between them attractive or repulsive? That means they'll attract one another. If it is opposite, they'll repel one another. Here, because the direction of a current, the direction of a charge is the same, which means that they are going to attract one another. So it is an attractive force. Interpreting graphics, the direction of a magnetic force on a current conductor, direction magnetic field here is always from north to south. So direction magnetic field, direction current you could do this, direction magnetic field, current this is a wire out of the palm, that is going to be out of the page, outward. Out of the page and outward, Z positive on and these are extra diagrams just to help you understand what it is. This summary, it would be best to go through the summary as well. Well, how can you increase the strength of a magnetic field inside a solenoid? Magnetic field is solenoid mu naught n I what can we do, for example, to increase the magnetic field of a solenoid in here? Increase the number of coils per unit length, increasing this one together, that would be one of them, of course, that is directly proportional. Increase the current, that is also true. Place an iron rod inside the solenoid, that is the only thing that is not in the equation, all of the above, so that would be the correct answer here. I'll use the diagram below to answer question 2 and 3. How will the electron move once it passes into a magnetic field? This electron goes into a magnetic field and then it makes half a circle and then comes back parallel to the way that it went. Something like this. It will move or it will curve to the right and then continue moving in a straight line to the right. That would be incorrect, Baba, because that is the same thing if you're saying that is how it goes and then just goes in a straight line. Now, that is not the case in there. So not this. This is curving to the left. That is opposite to this. That is also not true. It will move in a clockwise semicircle. So will it be clockwise or counterclockwise? This is something that I need to do for you here, The magnetic field, directionally magnetic field into the page. Directionally electron you can see up. Because it is electron, so it's the back of the hand. It is pointing to this side here. This is how it is going to, for example, make a half a circle and then come out. But is this half a circle, is it clockwise or counterclockwise? It is clockwise. Positive which would have become counterclockwise. I think it's the magnitude of force on an electron once it passes into magnetic field of Zamasana. Magnitude, don't choose negative. I think there's nothing special about any of these questions here. This is also find the direction of a magnetic force on the wire. You can use the right hand rule and that's it. Well, I used the diagram below to answer question 7 to 9. Do wire mane baba. You can see that wire 1 and wire 2. Wire 1 carries current 1, wire 2 carries current 2. And you can see there. What is the direction of a magnetic field, B1, but at a location of B2, at a location of wire 2? But what do you mean by the location of wire 2? Is that wire right to left here, yes or no? This is the right side and this is the left side. استاك واري دوم لچان لايتي بابا للاي راستي عن سبيتي للاي راستي كاتا دايركشن magnetic field دي بابلين للاي راستي واري direction كيكو. So باش because the direction of a current is downward good man who baba place your thumb in the direction of a current kata the current this is how it is curling up right so it is going into later direction magnetic field okay باشا ما later direction magnetic field okay baba it is into let's just try something nice maybe actually the direction magnetic field okay into the page kata later of course is going out of the page so let's just do this one too and yeah that's too much. Let's try once. Try nice for once. My later direction magnetic field okay, Baba, is into the page because this is how it is going on. Yeah. What about at this point, Baba? If it is into the page here, obviously like indicator is going to be out of the page. Yeah. So later into dash out of the page. Kata direction magnetic field wari kam lashweni location wari dum the kata Baba. It is out of the page because this is how it is going. It just kind of like curls behind and then just comes back right here. You can see that right here it is out of the page there. Kata it is going to be into or out of the page, Bitman D out of the page. Basha, what is the direction of a force on wire do as a result of one here? This also, Baba, is something very interesting. That's now the current in these two are they same direction or opposite direction? Opposite direction. And if it might get opposite direction, will they repel one another? Kata, in which way the wire do is moving? Is it moving to the right or to the left? Isn't it repelling? You don't need to use any right hand rule here. But it is repelling. Basha, if it is repelling, in which way is it now? Basha, is it to the left, to the right, whatever? It is to the, no, my bad. That's to the right, okay? So to the right, and that's it. So, Gutman, of course, this wire is moving to the right because of the magnetic field of this wire. Basha, what about if they ask about this one here? What is the direction of a magnetic force on wire 1 as a result of magnetic field of wire 2? Okay, this is going to the left. But that is not our case in here. What is the magnitude of a magnetic force on wire 2, Baba? Madam tala magnetic force wire 2, قد ما طلع force يدو دكاتة BIL معنى أنا همي يدو بس magnetic field دك external Chio external magnetic field they provide the that is wire 1 of course. Describe how you can use the right hand rule to determine the direction of a magnetic force around a current carrying wire. Madam current Baba, you and place your thumb around, like in the direction of the current, just curl around your fingers, curl your finger around the wire. That'll be the direction of a magnetic field. Draw a diagram showing the path of a positively charged particle moving in a plane of a piece of paper in a uniform magnetic field coming out of the page. Basha? Coming out of the page. But, obviously, there's no drawing coming or will be in Rosari, but if the magnetic field is out of the page, Baba, these are out of a page for a magnetic field. Let's just draw more. Uniform magnetic field. Basha says, so how exactly, like, will it go? Was it clockwise or counterclockwise? This one moving in a plane of paper, uniform magnetic field coming out of the page, Basha. Also, let's talk about this one here. If it is moving, bubbling, this is a bubbling positive charge, or it could be, actually, let's do that at the bottom, perhaps it might be easier a little. Zor Bash. But my need about directionally magnetic field is out of the page, and let's say that this positive charge is moving into a magnetic field. Like, how will it go? Obviously, it will end up moving in a circle. When this circle, it is either clockwise or counterclockwise. So how do we know which way is it? Let's say, is it moving? Let's just find out. The first time that is going into a magnetic field, Baba. Watch this. The first time it is going into magnetic field. Magnetic field, this is into the page, but here is out of the page. So this is what I need to do here. So, for example, if I do this, right, that is, you can see that it is the direction of a motion here. This is the magnetic field, kata. The magnetic force is going to be to the left one, yeah. So if it is going to be to the, to this side here, that's what I meant, Yani, towards me, because it is going to be out of the palm in here. So this is how it is going to move. I believe, I think I draw this one a little bit early here. So this is how it is going to move at this point here. Asha, this is how it is going to move. Now, once it is moving, let's say this way, because this is what we said, right? That is how it is going to move in that direction here. Now, after it is moving in this direction, Baba, Timasha, and you could do this again here. The direction of a magnetic field is out of the page. this direction of motion here, so it is going to move down one, yeah. So at this point, if it is moving down, so that was the magnetic force in here. So if it is going to move down, this is how it is. Then now it is going to move in a circle like this. So obviously it is going to be what? It's going to move in a circle. So there's your magnetic force always directed towards the center. Got a direction motion like it is going to be clockwise here. Got a positive charge moving into a magnetic field that points out of the page. It is going to be clockwise in that plane of the page, and that's it. You can see over there. Later short response on here. I believe it's worth it. It says a proton charge K1 there, mass K1 there is uniform magnetic field down there. The proton moves in a clockwise. It says in a clockwise circle with a tangential speed on there. What is the direction of the magnetic field? Explain how you determine that. First of all, it says proton, and it's also moving in a clockwise direction here. When a charge moves clockwise or counterclockwise, you basically have two directions, like for example, immediately. This says clockwise, and it's positive charge. Let's take a point right here. That point that you did, point about the direction velocity is tangent. That direction velocity, force is always towards the center here, provided by magnetic force here. So now you can find the direction of a magnetic field. It says what is the direction of a magnetic field? One B, V, and also magnetic force. V is X positive. Force it is Y negative. That is going to be Z1. Is it Z positive or negative? You could just do that one. And because it's positive charge, you could do that here. According to this, that's what happens here. You can see that magnetic force velocity to this side here. Magnetic field is out of the pitch, or Z positive. How did you do that? You could say by using the right hand rule, of course, by placing my thumb down, pointing it downward, because that is the magnetic force at that point. Velocity to the right, you could say, or to X positive, the magnetic field would be Z positive out of the pitch. What is the radius of a circle, Because we have circular motion, centripetal force, magnetic force, F centripetal, magnetic force, QVB, centripetal force, mass times tangential squared less radius. What is the radius of a circle? Now, place or make the radius the subject. That is going to be down V squared tangential squared and said QVB. Now, just plug in the numbers, you can find the radius, and that'll be it. That'll be the answer to this question. We can just want to cancel. Okay, and these are been in Wrya as well. These are some extra Wrya questions for you to practice them, and that is the end for this session. Make sure that, of course, you solve these Wrya questions, because some of them are easy. Of course, it gives you a boost of energy. Some others are a little bit of, you can say critical, or requires critical thinking. That, of course, helps you a lot to go or to get over these challenging questions. That's the end for this session. Till another session, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.